Yeah, so I'm Robin. Yeah, I'm a civil servant, so I work for the UK Ministry of Justice. So this is a talk about Splink, which is our free and open source software for record linkage at scale. I guess just a couple of preliminaries before we begin. There's lots of time left at the end for questions. I encourage you to drop questions in the chat as we go, and we can talk about them at the end. But if you do have something quick that's like very relevant to the slide that's up, feel free to interject, and I'll answer as we go. Another caveat as we go, as we look through some of these slides, there's some simple example data on some of the slides. All the data that you're going to see is synthetic, like fake data, apart from my name, which appears occasionally. So I thought I'd start with a sort of 3-minute tour of the key points, just to hopefully kind of draw you into this talk. So I'll go quite quickly here, but we'll dig into all of the detail later. So we're going to be talking about Splink. As I mentioned, it's a free and open source tool for record linkage. That's within the Verlegi Center framework. That's a statistical framework. So it's been developed by a group of civil servants at the UK Ministry of Justice to handle some of the largest record linkage tasks in government. It's a highly customizable tool. So in Splink, we don't make any assumptions about the entity type that you want to link or kind of what data fields you have in your data set. As a result, the tool has to be very flexible, so the user has a lot of control over how their data is compared, how the model is trained, and so on. As a result of that customizability, it's capable of high accuracy linkages across quite a wide range of scenarios. Splink is specifically designed to be able to handle big data sets. Several users, including ourselves, have successfully linked over 100 million records with Splink. And it's also pretty fast. So in our benchmarking, we could get it to make a billion quite complicated record comparisons in under 2 minutes. The libraries, I guess it's been doing quite well. We've seen quite significant international adoption. So it's been used in government and academia, the private sector, and it's now been downloaded over 8 million times. So just a few more slides to sort of draw you into the talk. I think there's often quite a legitimate concern within government about the use of black box sort of AI models. Certainly the case with Splink, where if we're linking data, we're often linking person records with personal identifiers. And as a result, as we built Splink, there's a real focus on sort of diagnostics and explainability. So we want to understand exactly what our models are doing. Once we've estimated the parameters of the statistical model, we want to know whether they're right and diagnose any problems. So within Splink, we have quite a wide range of interactive visualizations, charts, and other tools to help answer these questions. And there's just some more of the kind of variety of visual outputs that you get from Splink. Finally, just for these summary slides, I wanted you just to have a bit of a better sense of what Splink actually is. So it is a code-based tool. It's in Python. It doesn't have a graphical user interface, so you use Python code to configure your record linkage models. The code is relatively succinct. So on this slide, we're configuring, training, and then using a record linkage model in, I think that's 43 lines of code. I'm quite conscious here I'm speaking at R Govys, not Python Govys. But I guess what I'd underscore here is that really Python is just providing this high-level interface into configuring your statistical linkage model. So to use it, you really don't have to be a Python expert. There's loads of examples online in our docs of different linkage models. So if you are an R person, I would suggest kind of taking a look at an example and adapting it to your purposes. This decision to build everything using code, it was very deliberate because we think that there are a number of advantages. Probably most of you on the call will be on board with this already. But some of the key things are if you do your record linkage in code, it makes it fully reproducible. It also means you don't have to go all into use Splink, so it can complement other tools and approaches. So you could use Splink for scoring, but not clustering if you wanted. If you just wanted to do some analysis of blocking, which we'll see later, you could use Splink for that and a different record linkage package for other parts of your problem. Another quite important thing for us is because Splink is just Python code, it works multi-platform, by which I mean it'll work on like Windows, Mac, Linux in your cloud provider. that's been a real kind of important feature for us, because Splink has been designed for use by different government departments here in the UK. And possibly similar to what you'll all be familiar with, every kind of department and agency has a different IT infrastructure. So we wanted to be careful right from the get-go to make sure that it would run on quite a wide variety of IT infrastructure. Okay, so that's it for the sort of very quick world run tour. So let me outline the plan for the rest of the talk. So the overall aim really today is just to introduce you to Splink, and I'd like you to come away with a sense of what this software can do and how you may be able to use it. So we're going to take a look at how it works. We're going to have a quick step-by-step example, and we'll see a little bit of code, but I'm really not expecting you to sort of read and understand the code I'm showing. It's just to give you a bit of a sense of how to get the outputs we'll see. You know, there's documentation and examples online that you can use if you want to get stuck in. We'll also at the end take a quick look at alternative tools, specifically the FastLink package. One other little caveat today, which is kind of exciting. Today's is the first time I'm going to be talking about Splink 4. So if you install Splink today, you'll get Splink 3. We've been working over about the past 6 months on Splink 4 and its pre-release, which means it's kind of in beta. So I've updated this talk with all the code you'll see is Splink 4 code, which going forward is what we recommend people use. If you install it today and want to use Splink 3, the syntax is very slightly different, but there's documentation online that can kind of bridge the gap. All right, so moving on to sort of the aims of Splink. I guess during my career, I've worked on record linkage on and off for a number of different organizations in government. And one thing that really stood out with me is that every organization seems to have a different solution to record linkage. It's a really pervasive problem. Everyone has this problem of different data sets where they don't have unique identifiers. But there doesn't seem to be like a really easy, or there didn't seem to be like a really easy and free off-the-shelf solution to that problem. Some agencies pay an awful lot of money for proprietary software. Other people were writing custom code, and there just seemed to be quite a lot of reinventing the wheel. And I'm certainly guilty of reinventing the wheel on at least 2 occasions historically. So when I was working at the Ministry of Justice and we were working on a project to improve data quality, I saw it as an opportunity to, like, third time lucky. The kind of idea here is to try and solve the problem once and solve it well. And that is to kind of produce a very general and flexible solution that could be reused in many different linkage scenarios. Something that doesn't make any assumptions about the type of data being linked, whether that be a person, an address, a business, you know, the different entity types you could link, which would enable it to be used in government, but also if people wanted to, by academics and in the private sector. So I suppose if we're successful in this, we're hoping that it'll take a lot of the heavy lifting out of record linkage. It'll allow users to concentrate on the modeling aspect of their linkage problem and understanding the parameters of their model, with the kind of common calculations taken care of in a way which makes them fast and scalable. And also with a methodology that aligns to the literature in terms of concepts and best practice. So, you know, when we started out on Splink, we did a big literature review to understand what were the best statistical techniques and what already existed. So I think, like, all of this that I've just been kind of talking about is well captured by this quote from William Winkler, who worked for the US Census Bureau, writing in 2018. So he says, by the mid-1990s, national stats institutes had failed in possibly 30 attempts of initial development of Felighi-Center systems. So he's pointing to these kind of many failed expensive attempts to build something like Splink. And, you know, I'm not at all claiming here that Splink is the only solution to this problem or solves the problem once and for all. But to my knowledge at the moment, it's probably the kind of closest thing to a solution where multiple different organizations can use this. So I thought it's also sort of interesting to think what's changed between sort of the mid-1990s and now that made something like Splink possible. So he was writing in 2018. I guess that was kind of around the time that open source collaboration and tools like GitHub was really taking off. Certainly it hadn't been taking off in the kind of mid-90s. And really for us, that's just made all the difference. So I think we started in early 2020 on Splink. And what we found is by putting all our code in the open on the internet for free, it just attracted a lot of collaborators, a huge number of people internationally, including experts from a variety of national statistics agencies and from academia. If it just felt like because we were sharing everything we were doing, people were much more keen to sort of help us out, basically. And I think it's also helped that the development team are civil servants, so that's avoided any potential issues with sort of commercial incentives or kind of for-profit incentives. In addition, another thing that's changed is that Splink is itself built on top of a lot of open source data analysis tools that simply didn't exist a few years ago. So a lot of the speed comes from these recent developments in speeding up and parallelizing analytics workloads. So moving on, this slide covers a little bit about how Splink is currently being used, as far as we know. We think it's probably used more widely, but people just don't tell us. So it was developed by the Ministry of Justice for something called the Data First Programme. If you Google for that, you'll find more information about the Data First Programme. And as part of that programme, to improve data quality, we linked over 100 million records from the courts, prisons, probation, family and civil parts of the justice system, and made this linked data available to academics for research in a secure environment. Subsequently, Splink has been used by the UK Office for National Statistics as part of the methodology for the 2021 census, also their business and demographic indices, at least 4 other government departments here in the UK and multiple areas of local government. More internationally, the German National Stats Institute, the Uruguayan one, the Chilean Ministry of Health, European Medicines Agency, kind of a few more here. The collaboration aspect has been great too. So we've had significant contributions to the code base from the Australian Bureau of Statistics, also from Databricks and from some academics. We know that Splink is currently also being trialed by the US, New Zealand, US and Cabo Verde National Stats Institutes. So they're sort of giving it a go, seeing if it's appropriate for their use cases. Also by researchers in a number of top universities. It's nice when we get a citation on published papers, and we know it's quite widely used in the private sector now. Okay, so we're just going to change gears a little bit now and move on to looking at kind of what Splink does. So at a very high level, Splink takes as an input one or more tables that lack a unique identifier. So that's kind of the table at the top here, where we've got several records, the top 3, which are probably the same person, and the bottom 2 are probably the same person, but they don't have a unique ID. So, you know, how do we know? That's why I've got the question marks against person ID on the right there. It then will generate pairwise record comparisons. So that's the middle table on this slide, and predict a pairwise match score using something called the Filegi-Santa model, which is a sort of statistical formulation with a maximum likelihood function and that sort of thing. Those pairwise scores are useful in some contexts, but often what's more useful is to cluster them. So the pairwise table is just telling you that, let's say 1 is 2 and 2 is 3. Which means that 1, 2, and 3 must all be the same. And so actually, by clustering, which is gives you the last table here, what you can produce is a sort of estimated person ID. So one way I like to think about this is that the problem is that we lack a unique ID for our entities. That's the question marks in the top table at the right. And what Splink does is it will produce you an estimated unique identifier, which is the person ID column in the bottom table. So let's just dig a bit deeper into this. So what I'm going to do is I'm going to use a simple example to talk through this methodology step by step, using some of Splink's diagnostic charts. And this is going to serve a sort of dual purpose for the talk. So it's going to help me carefully explain what the linking methodology is in Splink. But it's also going to help me demonstrate how some of the charts produced by Splink will help us explain our models and diagnose problems. So in the Filegi-Santa model, we start with pairwise comparisons of input records. So we look at the records coming in and we compare them pairwise side by side. So we've got an example on this slide. There are usually thousands, hundreds of thousands, often many millions of these pairwise comparisons. So for each column in the model, so in this case, first name, surname, and so on, what we're going to do is define a number of discrete similarity levels for that column. So that's things like, is it an exact match on first name? Is it a fuzzy match on first name? Is it no match on first name? Once we've done that, we're going to estimate things called partial match weights for each of those discrete similarity levels. And then those partial match weights are then combined to produce a final match score. So this is just talking through the methodology again. So the first step is to assign each column to its similarity level. So for instance, we can see here that the first name has been categorized as Jarrow Winkler. Actually, here it's just Jarrow similarity of greater than 0.9. The surname, that's because Robin is misspelled in the second one with a Y rather than an I. The surname is an exact match. We can see that the postcode is an exact match. Postcode is the equivalent of a zip code, basically. And here we've got a mismatch on the gender comparison. Incidentally, there's a little link on the slide. I'll put it in the chat. That you can, this is all part of a sort of interactive explainer online. So if you want to give that a go, if you click through the link, you can actually edit these values and see what happens. So the next step is to look up the corresponding match weights for each of these categorizations. So if we use first name as an example here, in this model, we've chosen to split the first name into these three discrete categories, each of which corresponds to a match weight. And these match weights are shown in the chart in the middle of this slide, and this is called a partial match weights chart. So for example, we can see that an exact match on first name has a stronger match weight than a Jarrow fuzzy match. So that's because the top green bar has a higher partial match weight, a higher positive partial match weight than the middle one. So that's what you'd expect. A exact match on first name is more evidence in favor of a match than the Jarrow, the kind of fuzzy match on first name. We can also see here that the non-match on first name, which is to say it's not an exact match and it's not even a fuzzy match, the non-match on first name has got a negative match weight, which is kind of to be expected because if the first name doesn't match, that's evidence against it being a match. So these partial match weight charts, they sort of act as a lookup table for the match weight. So we can use this chart to find the fuzzy match weight for Jarrow similarity of greater than 0.9. In this case, this is a match weight of about 6 reading off the chart. And what that means sort of intuitively, I guess, is that if we observe a fuzzy match on first name, it's about 64 times more likely that the original records are a match. Okay, so what I'm going to do now is I'm going to take that chart in the middle of this slide and I'm going to stack them on top of each other for each of the different columns. So we still have the first name one, but we now have we still have the first name one, but we also have the surname, postcode, and gender one. What this chart does is basically is a nice summary of the overall record linkage model. So it shows us all of the match weights. And it also helps us check our intuition as to whether the model is doing what we expect. So just like picking out some messages here, we can see that the postcode, the exact match on postcode, which is the red bar, that is the strongest positive match weight in the whole model. So we can check our intuition on that. There's a very large number of postcodes in the UK. That means it's a high cardinality variable. And that means that if you match on postcode, that's very strong evidence in favor of a match. Because there's a greater number of postcodes than there are like the variety of first names or surnames, postcode has a stronger match weight than either surname or first name. So intuitively, it makes sense that postcode has the strongest match weights. Another one we could look at to check our intuition is gender here. So gender, we can see that an exact match on gender is very weak evidence in favor of a match. So that's the gray bar in the kind of bottom portion of this chart. That makes sense, right? Because if you have two people that you pluck at random from the population and you observe the fact that they're both female, say, that's not very much evidence at all in favor of the fact that they're the same person. It's just a coincidence most of the time. But this also illustrates something interesting about non-matches here. So whilst it doesn't help much to know that two people have the same gender, if you have high quality data on gender, it can often be the case that if the genders mismatch, that's quite strong evidence against it being a match. And that's certainly the case in the criminal justice system here in the UK, because we have a female estate and a male estate. And so the data quality for the gender field is very high. So if it mismatches, it's generally quite strong evidence against them being the same person. Okay, so to compute the overall match score, we simply need to add up these partial match weights, and we can show this graphically on a waterfall chart, which is an attempt to visualize how the overall match weight for a particular pairwise comparison was computed. So this is just adding up the column-specific match weights. So if we read the waterfall chart here, so looking at the x-axis and reading from left to right, we've got the different column comparisons: first name, surname, postcode, and gender. And on the y-axis on this chart, we have match weight. Where match weight is negative, that means that we're saying the record comparisons are unlikely to be a match, and where it's positive, or the more positive it goes, the more likely they are to be a match. So let's just read through this chart slowly, because it gives a pretty good summary of how the Foleggi-Sunter model works. So on the left-hand side, the blue bar, which is labeled minus 19.9, we start with something called the prior. That's a Bayesian prior, in the sense that it represents our belief that two records drawn completely at random are a match. So we start in very negative territory, because it's very unlikely that if you just pluck two records from your data set, they're a match. But then in the orange column on the waterfall, what we've done is we've observed that the first name is a fuzzy match. We've looked up the orange bar from our partial match weights chart, which is 5.6. And so we move upwards in match weight space by 5.6 for the fuzzy match on first name. We then have the exact match on surname. So we move even higher. That's the green bar. We then have a very strong positive match weight on postcode because it's a very high cardinality column. But then we notice that there's a mismatch on gender, and that fairly significantly reduces our match weight. And we end up with a final score here of 3.93. That corresponds to, I think, a match rate of something like 96%. But what this model is saying is that these people are probably the same person, but we're not really sure. You can imagine that if gender had matched, rather than being at like 0.96, we'd be more like 0.999 or something. So under the waterfall, I've just got the sort of the corresponding algebraic equation where we're just adding up the match weights to get the final match weights. So really, like the model itself is very simple. You're just adding up match weights. The interesting bits are more like, where do these match weights come from? How do you get them? And how can you customize your model? So that leads us on to customizability. So hopefully that all helped clarify the methodology. But I think it's put us in quite a good position to talk about customizability and where that comes in, because the user gets to control all of the things we just talked about. So in a nutshell, all of the definitions of the comparisons are in the hands of the modeler. So we were talking about the Jarrow of being greater than 0.9. The user of Splink gets to decide all this stuff. So in the above example, we made the comparisons really simple. The first name was this 3-level comparison. It was either an exact match, Jarrow match above a threshold, or everything else. But you can have as many levels as you want, and you can define them exactly how you want. So for example, when designing a comparison for names, you could estimate different match weights for a D-metaphone match. So D-metaphone is similar to SoundX. A Jarrow-Winkler match at different thresholds, whatever you wanted, you can get really creative with it. If you were doing a zip code, you could estimate different match weights for different geographical distances. If you had geocoded your zip codes, you could do a Levenstein match in case somebody had just done a typo in typing it out. You can even define things like a comparison that looks at arrays of zip codes if somebody has lived at multiple addresses and looks at whether there's like an intersection in the zip codes or something like that. And in addition, for any level, you can define term frequency adjustments, which help ensure that a common name like John gets a different match weight to a more uncommon name like Robin. So Splink will then estimate different match weights for each level, and that gives your model a lot of nuance when it comes to scoring. Similarly, there's a high degree of customizability in terms of blocking rules. Blocking rules are the part of Splink that helps you optimize runtimes. Okay, so hopefully at that stage, you're starting to get a bit of a sense of what Splink does. What I'm going to do now is just quickly run through an example of how it's used. And the idea here very much isn't to give you a full-on tutorial, but it's just to bring things a bit more to life, to show you some of the functionality, to show you that you don't really have to write too much code to get that functionality. What we're going to use is a data set that's built into Splink. Thanks for the question, Richard. I'll address that at the end if that's all right. Okay, so we've built a couple of fake data sets into Splink just so it's very quick for people to have a go with Splink without having to find a data set to use. This one is it's synthetic data and it's very rough and ready. We haven't done a very realistic process of generating duplicates, but we can see here that we've got this group of records of Robert Allen with kind of typos, and we've got Rob and Robert. We've got nulls for some of the records and things like that. So we're going to use this just for the purpose of these examples. So like any good statistician, the first thing you should always do when thinking about applying a statistical model or thinking about doing any analysis really is do exploratory analysis. So the first thing that we're going to do with this data set is profile our data. And within Splink, we built some tools that produce some very common visualizations that try and highlight the parts of the data which are particularly important specifically for the purpose of data linking. So these charts, we're going to profile the first name and city column of the data set. That's the code on the left-hand side. But what we're really looking here is for skew. So skew here means if we have some first names which are very common and others which are very uncommon, we need to make sure that the model can take account of that, because if you take two random people from the population and they both have the name John, that's not a huge coincidence. But if they both have a really unusual name, it becomes much more of a coincidence. So this chart, just very broadly, is telling me that there's quite a bit of skew in the first name column. And the second chart is saying that the skew is even worse in the city column. That's kind of to be expected here in the UK. So we've got loads and loads of records from London, fewer from Birmingham and some of the other bigger cities, but then there's a really long tail to that distribution. The next thing we want to do generally is understand the consequences of blocking rules. So blocking rules in the context of record linkage are, there's a problem in record linkage where if you have even 1,000 records, if you need to compare every record to every other record, that's 1 million comparisons. And so you can imagine that grows like the relationship is n squared as the size of your data set grows. So you might be able to do 1 million comparisons with 1,000 records, but as soon as you're putting in 1 million or 10 million records, you can't compare everything to everything else. It just gets too massive. So what you have to do, the usual solution to this is use something called blocking rules. And what they do is they sort of select a subset of comparisons where you're more likely to find matches within them. So an example of a blocking rule would be to find all record pairs where first name and surname matched. And another blocking rule might be to find all record pairs where date of birth matches. And by applying those blocking rules, you sort of eliminate like a very large percentage of all of the record comparisons, because the vast majority of them are just completely different and don't match at all. But one of the first problems you hit in a record linkage problem is, well, what are those blocking rules? What are the blocking rules which are going to give me a reasonable number of comparisons that aren't going to generate trillions of comparisons, that are going to give me a reasonable sort of set of potential matches? So in Splink, we've got quite a few tools for doing blocking rule analysis. One of the ones is shown on the slide here. So this one is telling us that if we were to block on first name and the first initial of surname, then it's telling us, for this data set at least, we're going to generate a total of 1,700 comparisons. We can also, in the table in sort of black and grey, take a look at the biggest blocks. So for this data set, the biggest block, if we block on first name and the surname initial, is Theodore M. And we can see that that's going to create 81 comparisons comparing all Theodore M's with all other Theodore M's, which means that there are 9 of them that result in 81 comparisons. So that sort of blocking rule would be fine for this small data set. In this data set, even if you blocked on city, which doesn't sound too bad with your 1,000 input records, because there's so many Londons and Birminghams in this data set, that alone would result in 37,000 comparisons. So it's these kind of tools that sort of help you check stuff before you shoot yourself in the foot later and generate sort of 1 trillion comparisons or something by accident. Once you have figured out your blocking approach, the next thing you do is you configure your comparisons, which is kind of like the Linkage model. So in this example, we're configuring the link type to be a dedupe only. So Splink supports deduplicating a single data set, linking between two data sets, or doing both simultaneously. That would be the case if either or both of the data sets themselves had duplicates and you wanted to link them. That would be a link and dedupe. So here we're defining our comparisons where we're telling Splink we want an exact match of first name comparison with term frequencies enabled. We want Jarrow Winkler at thresholds on surname and so on. The little GIF playing at the bottom there is actually one of the nice new features of Splink 4, where before you had to remember all of these keys like link type and blocking rules to generate predictions and type them all out by hand. And it was really annoying, but in Splink 4, it all auto-completes for you, as you can see there. So you start typing and you get it auto-filled. So once we've defined what model we want, we've defined the comparisons, which are those discrete levels. The next step is to estimate the what we call lambda, but that's the Bayesian prior, otherwise known as the probability that two records taken completely at random from the data sets match. I'm not going to talk too much about sort of the estimation methodology here, but you can see each of these estimation procedures is a sort of quick method called in Splink. The next step here is to estimate the U values of the model. So for those of you familiar with record linkage theory, what we're estimating here is amongst records that truly don't match, how often do you observe the scenarios, which is kind of like how often coincidences occur. So how often do you observe two records with a match on first name, but they're not actually the same person? There's a direct estimation approach for this in Splink. And I think in the interests of time, I won't describe exactly how these estimation procedures work, but please do feel free to ask questions at the end about them. So generally, once we've estimated the U values, that's the first point at which we would probably take a look at our partial match rates chart. So this is the chart we saw earlier. And what we're looking for here is whether it looks reasonable. So here we can see that if the comparison level is an exact match on first name, then the comparison is about 164 times more likely to be a match. That might be a bit difficult to check in terms of intuition. So I read that off from the match rate description in the tooltip. But if we were looking at something like month of birth, then you would expect that if the month of birth matched and the comparison was an exact match on month of birth, then the comparison would be about 12 times more likely to be a match, because obviously there's 12 months in a year. So these are some of the tools that just help you sort of check your intuition on whether the model's done something sensible. The next step is to train the M values of the model. So this is saying amongst truly matching records, how often do you observe your exact match? How often do you observe your fuzzy match? And because these are saying like amongst truly matching records, how often do you observe these scenarios? You're immediately in like a catch-22 scenario here, because the whole problem you're trying to solve is to match your data. You generally don't have labeled data. So it kind of looks like we're stuck here because we need to estimate these M values of the model, but they require us to know which records are matches, which is the whole problem we're trying to solve. But it turns out that there's an estimation, like an unsupervised estimation procedure called the expectation maximization algorithm that allows you to do this. So in most cases, we recommend using EM for training the M probabilities. If you do happen to have labeled data, then great, you can train the model directly from your labeled data. So that's just the code for how you do that. And then we would typically, if we were doing this, we would take another look at the match rates chart here to check that everything is still looking fairly sensible. At that point, we've got a fully trained model. We could actually save that model to disk at this point and load it in again at a later point. You can just save the whole model as a sort of .json file. But here we're going to train and then immediately use it to predict. When you've done your predictions, you get out a data set that looks like this. And we try and format this data set to look to be kind of like a bit easier to read by putting, so we've got these pairwise record comparisons in the output, and the match probability column and the match weight column are telling us how likely they are to be a match. And we try and set the values against each other. So like first name on the left-hand side of the comparison and first name on the right-hand side of the comparison are being set against one another. But nonetheless, this table ends up being pretty big and pretty hard to read. So we've developed some visualization tools to help a little bit more there. The main one we use is the match weights waterfall chart. So that's the same chart we kind of saw earlier. But here we have one which is a sort of generated from this kind of real, well, the fake data set, but it's generated from a real Splink model. Here we can see that this is a record pair, which ends up being a strong match because we've got a match on Amelia. We've got a negative match rate on surname, but that looks like a kind of typo on Porter versus a kind of misspelling of Porter. But then we've got a match on their date of birth, their city, and a non-match on email, but it's kind of like the emails are similar. The other thing that we can observe here is that there's a term frequency adjustment on the city. That's what we set up earlier. The city here is Portsmouth, which is at least a relatively small city here in the UK. So what it's saying is, well, here that the average match weight on city is 3.42. But because it's an exact match on city and it's a fairly unusual city, there's an additional up weighting essentially of 1.68 on city to increase the match score a bit further. So for this particular record pair, this example one, we end up with the algorithm telling us that this is a very strong match. Okay, I'll skip that one. Yeah, and you know, just back to the code. So that's just a summary of all the code that we just ran, just to give you a sense of like the totality of the code to get those results is quite small. So that kind of example, it covered, I guess, some of Splink's core functions. There's a lot more stuff built into Splink that I don't have time to cover today. The main areas are really like more blocking analysis, accuracy analysis. If you've got some labels and you want to know how many like false positives you're getting, that sort of stuff. Splink will do clustering and generate cluster metrics for you. There are some really nice interactive diagnostic dashboards you can use to understand your results a bit better. And there are also alternative estimation procedures for the different parameters. One bit in particular I can't resist just showing a few of is the interactive dashboards, just because I think that they're some of the more powerful parts of Splink, and we put a lot of work into making them as useful as possible. So the first is a threshold selection tool. So often one of the big problems of record linkage is after you've trained your model and you've got your results out, generally, although you've got this continuous match weight score, which is telling you, you know, some have a higher score, some have a lower score. Generally, you have to pick a threshold and decide above a certain match weight threshold, you're going to accept them as matches, and below that threshold, you're going to reject them. But the problem is often picking that threshold. And this dashboard allows you to understand as the threshold changes, how it affects precision, recall, false positives, and so on. The next dashboard that we use all the time, this is probably the first thing that we look at after we do some predictions, is called the comparison viewer dashboard. And this picks out example record comparisons really across the spectrum of match scores and allows you to inspect them using a table and waterfall chart. So that gives you a really quick way to explore the predictions the model is making, from some of the like really certain predictions down to some of the like ones that it thinks are definitely non-matches and everything in between. And that just really quickly gives you a bit of a sense of whether it's kind of working or kind of not working at all. But it just allows you to, and also helps you to kind of pick out edge cases where maybe the model hasn't done what you expect. And sometimes then you'll iterate back and maybe improve your data cleaning rules and that sort of stuff. There's also a cluster dashboard that allows you to explore the clusters predicted by the model to see whether they look sensible and whether you've got any unusual cases causing problems with the model. So in the cluster in this slide, all of these people are supposedly the same person, but we can see that they're not really heavily interlinked. The metric is called the density. The density of this cluster is really low. And that can kind of tip us off to the idea that something might have gone wrong with our model here, because this kind of looks like 3 different people from the cluster chart, but it's all been merged into one. So what we would tend to look at here is explore some of those links that are sort of between the 3 kind of central or the 3 distinct clusters, and see whether they look like true links or whether there's something going wrong there. Okay, so I just want to delve a little bit more now. We're almost finished, actually. I want to delve just a little bit more into the technical implementation of Splink, just to pick up on some interesting features. Particularly, I want to talk a little bit about why Splink is quite fast and why it's likely to continue to get faster in the future. And also why we think that this Splink performance isn't a kind of dead end that will eventually need replacing, why we think it'll get faster in the future. So just a very brief description of how Splink works. So Splink is a Python tool. What it's actually doing is it's generating SQL statements that implement the Fellagy Center record linkage model. So what that means is that the computations, or at least the big ones, they're not actually done by Python at all. The SQL is then submitted to a backend database for execution. And we support several backends: DuckDB, Apache Spark, AWS Athena, SQLite. So you get to choose which backend database you submit your SQL to. So why would we do that? Well, the reason is really that some database engines are just really heavily optimized for running these kind of workloads. So essentially, we as the Splink development team, we're sort of delegating the job of performance to the database engines. And the reason we're doing that is that modern data analytics database engines like Spark and DuckDB, they've just got a huge number of really complicated optimizations in them. Things like, basic parallelization to make sure that your CPU cores are used, but also vectorization to ensure that the way that your calculations are submitted to the CPU means that each core can perform multiple calculations at once. Also, out-of-memory computation is really important here. So all of your data doesn't need to fit in memory. All of this stuff is sort of way beyond our skill level in knowing how to do it. So we sort of delegate it to the database. And many of you will know in recent years, there's been a real explosion of innovation in this area with new engines like DuckDB, big improvements to existing engines like Spark. Data Fusion's another new one, which looks interesting. And they're all just competing with each other for higher performance. So one of the nice things about this is because Splink is just generating SQL and sending it to these engines, it means that we can easily piggyback on any new developments. So whether that's like a new version of Spark that's faster or a new database engine that's better, we can simply submit the SQL to the latest versions of the engines and get performance improvements. Actually, the history of Splink and looking at our performance tests through time really attest to this. Most of the performance gains we've been seeing have not been us optimizing our code so much as the database engines getting better and giving us better performance. Another important upshot of all of this in the government context is that it means that Splink is not strongly coupled to any particular IT system or infrastructure. So I think I said in the intro, it can run on-prem in the cloud. It even runs on a really underpowered laptop if you've got smaller data. And that just means that things like if Apache Spark happens to fall out of favor next year, or your organization doesn't support it or whatever, it doesn't matter because you can still use Splink with one of the alternate backends like DuckDB. And you can do that. The changes to your Python code are very minor to switch between database engines. And all of that was very deliberate in the sense that we were aware in the UK of the sort of nightmare kind of IT systems differences where everybody's using different cloud providers, different IT systems, has different security protocols. So we knew that we couldn't ask departments to change their IT in order to accommodate us, so we had to accommodate them. So it's been a real core focus of the team, making sure that we have this kind of cross-platform functionality. Okay, last couple of slides now. So I mentioned at the start I would do a comparison to R. I'm going to compare Splink to the FastLink R package, which many of you might have heard of already. FastLink is an R package for record linkage. It's in the Fellagy Center framework as well. And actually, we're just very grateful to FastLink because very much the first versions of Splink were a re-implementation of the FastLink methodology. We looked through their papers, which are great that they wrote on their methodology. We looked at the source code. And we basically implemented the same statistical methodology with a view to improving the performance on big data. I think since then, it's fair to say Splink has added new features. So to begin with, I guess our features were pretty similar to FastLink, but we've been actively developing Splink for a few years now. And FastLink development has been. I don't think they've added too much in the last few years. So I guess the end result is that Splink is pretty similar to FastLink if you're used to it already, but it's a lot faster, it's more customizable, which means effectively it has the potential to be more accurate. And it has a lot more features, particularly around graphics and explainability, so some of the charts we've seen, and clustering as well. So just in terms of a speed comparison, FastLink have got this really fantastic paper that explains their methodology mathematically. So if you're interested in this, really encourage you to read it. It's sourced on this slide. One of the figures in their paper is the figure at the top right here, which gives their running time comparisons. So this was a few years ago now, but when they developed FastLink, it was, at least according to this chart, the fastest thing out there. There is a package called record linkage in Python, and apparently one called record linkage in R as well. And what they were able to show in this chart is that FastLink was quite a lot faster than them with a single core, and vastly faster if you parallelized it across 8 cores. But nonetheless, the runtimes here are quite long. So FastLink was taking, like, I think it's about 450 minutes there on a data set of 300,000 records. And the other thing we can see here is that runtimes are increasing sort of exponentially. So it's not just a linear increase as the data set grows. In contrast, some of our benchmarking shows that Splink can now dedupe a 7 million row data set in about 2 minutes, admittedly on quite a large machine. But you know, still, even if you were doing it on your laptop, a lot faster. I think this is saying so the equivalent would be 16 minutes on like a fairly standard laptop in the chart at the bottom. And in order to do that, it's making 1 billion record comparisons. So it's not just that it's using blocking to only create a few record comparisons among those 7 million. It's creating 1 billion record comparisons and giving you your results back in those pretty short timescales. So last slide, just wanted to mention Splink version 4. I mentioned this a little bit at the start. So the code that I've been showing in this presentation has been Splink 4 code. It hasn't quite been released yet, but it will be in the next sort of 2 to 3 weeks, we expect. The benefits of Splink 4, it's very similar to Splink 3, actually, but we've been able to show it's a bit faster and more scalable. So if you have really big record linkage tasks, you'll have less problems with scaling those out. It's quite a lot easier to use. We think the user-facing API, the documentation are just better. We've got autocomplete everywhere, which we had in that GIF on one of the previous slides, so you don't have to remember what settings are called. If you want to give it a go, the link here is to like a parallel version of the documentation site, which is kind of showing the new documentation. So we've put that an alternative URL just for now. And you can install Splink 4, but you have to do a pip install and then give a specific version. Or I think there's a -- like pre-release flag that you can put on your pip install. But if you just pip install Splink at the moment, you will get Splink 3, because that is the latest kind of fully released version. Great. Yeah, so really happy to take any questions. Also, just in terms of collaboration, Splink is open source. We welcome collaboration. We've had about 50 collaborators so far who have actually committed to the code repository. If you just want to use Splink, feel free to reach out to me at the email address on this slide. We generally do our best to help support people getting up and running with Splink. If you have any issues with it or you want to create a discussion, we've got a discussion board at the GitHub there. But yeah, I'm very happy. Thank you very much for listening, and very happy to take any questions.
Great, thank you, Robin. That was fantastic. Every time I hear you talk, I learn more. But then I realize I have even more to learn. So, which is kind of cool. There's actually 2 questions in the Q&A. So I think you could see them. But
I'm just having a look at Richard's. So how would Splink work with some records having just first name, surname, and other with first name, middle name, and surname? Yeah. Okay. Yeah, it's a good question, Richard. So what Rich is asking, I think, like, if we make this question a little bit more generic, is that data quality means that sometimes data can appear in like the wrong place. So one thing that we often see is name inversions, particularly of names of people from other countries, because there are different sort of rules around what, or different conventions around what is the first name and what's the surname in different countries. So in this case, he's referring to sort of like a middle name being in the first name field in one of the records, but you can also have an inversion between first name and surname. That's exactly where the like customizability of Splink comes in. So because you get to define how your comparisons work, you can define one of your levels, one of your discrete comparison levels as, so the first one would be, does first name on the left-hand side of the comparison equal first name on the right-hand side of the comparison? So that's your exact match. But you could have another level for, does first name on the left-hand side of the comparison equal middle name on the right-hand side of the comparison, or vice versa. So you can basically tell Splink to look out for that specific scenario if it's something you're worried about. Did you have any follow-ups there, Richard? Or feel free to put it in the chat if you would rather. But in the meantime, I'll move on to Miriam's question, which is, how does Splink address missing data? Yeah, that's a really good question as well. So the default way that Splink addresses missing data is, so we were looking on those charts and we were looking at things like if first name is a match, it's evidence in favor of a match. If first name isn't a fuzzy match or a match, so it's like a complete non-match, that's evidence against it being a match. The usual approach for missing data is that if one or both sides of the comparison is null, so you've got like Robin versus null, null versus Robin, or null versus null, that's taken to be no evidence in favor or against a match. It's just an unknown. So you can actually, you don't have to go with that assumption, but people typically do. There are some scenarios in which a null, like an unknown, actually has a greater meaning than just we don't know. Splink gives you basically control over whether you want to train a parameter value for a null, or whether you just want to leave it as no evidence in favor or against. Did anybody else want to jump in with any questions?
I don't see any. And if somebody has something they actually would rather ask, not in the chat, but verbally, I think, Donna, we could unmute them, right?
Yep, just raise their hand.
Okay, Miriam just asked another question.
Yeah, that's another really good question, Miriam. So we actually take a slightly different approach within Splink to blocking. So Miriam asks, how easy is it to combine different passes of blocking results and assess their results? So I think what she's saying here is that it's very common to use multiple blocking rules. So if you imagine blocking on first name and surname, so that will create all comparisons where both first name and surname are a match. And that's great. That'll capture quite a lot of your matches. But if you have a typo in somebody's first name, then you'll just completely miss that match, because the comparison will never be created. If it's never created, it's never scored. So it effectively gets a 0 score. When we talk about different passes of blocking rules, I think what often people are thinking about is we'll block first on first name and surname, and then we'll do a second run where we block on, say, date of birth. And hopefully by blocking on date of birth in the second pass, we pick up on the typo on the first name, because we still create that comparison because we blocked on their date of birth, assuming it's correct. And now the model will take care of, well, it is a fuzzy match on first name, and so we'll still score it, and hopefully it'll still come out as a match. So the way that Splink deals with that is you actually give it a list of blocking rules, and it does it all in one. So the list of blocking rules in the example I just gave, the first one would be block on first name and surname. The second one would be block on date of birth. And the first operation Splink does is it creates all pairwise comparisons that fit to at least one of those blocking rules. So all the first name and surname ones, and then it adds onto that all of the date of birth ones, and it actually deduplicates that. So it doesn't, quite a lot of them might match on first name, surname, and date of birth. So it makes sure there's no duplicates in that list. And then it scores all of those all at once. In the results, there's a column called match key, and that column will tell you which of the blocking rules that pairwise comparison was generated from.
Thank you. Hey, Donna, I think Richard had raised his hand.
He did, but he put it down, so I don't know if he, so.
Oh, he raised his hand again.
He should
So,
be able to talk.
okay, go ahead, Richard.
Sorry, I had to get all the gibbons to do, and it had to inform me it's being recorded. So that, thank you. Great talk. I actually put it in the question and answer. Can you allow for the situation where you've got a variable in data set A, you know it's been recorded really well, and in data B, it's not quite so well? Like we have this situation in New Zealand with ethnicity, that we have some data sets where we've got the ethnicity from the person, and the other one, somebody has put it in. We had a particular case where we were matching death records, and the death record was by the undertaker. And so obviously we couldn't get an answer from the individual. So can it allow for that? You can put in some information about the quality of it?
Yeah, so the process of estimating your M values, the M values, so the M values of the model are amongst truly matching records. Like, for example, amongst truly matching records, how often does your ethnicity match exactly? Then if there is a concept of fuzzy matching there, how often does it fuzzy match? Amongst truly matching records, how often does it not match at all, right? So when you estimate those M values, the M values, the best way I like to think about them is they're actually a measure of data quality. So if your data quality is extremely high, you would expect almost all of your matching records to be in an exact match on ethnicity, right? So one of the nice things about the M values is that they're a really good summary of how good the data quality is. So in your case, the only bit I'm slightly hesitating about is because you've got like these two data sets, one which has high quality, the other has lower quality. But the mode that you use in Splink, there's a mode called link only, and that makes sure that the model is only creating between data set comparisons, right? It doesn't compare any records to within the data set, it's only between them. And so long as you've got link only on, then the M values, when they're trained, should absolutely reflect the poorer data quality of the second data set. So it should be, I think, correctly estimating the pertinent question to your record linkage model, which is when you create record comparisons between these two data sets, amongst truly matching records, how often do you see ethnicity matches? And that'll be predominantly being driven by the poorer data quality, I think, on of the second data set.
Actually, that's a good point, because you always think of, my job with record linkage is to link records. And as you started off with, you've got the EDA, and it would be a way of saying, I've got data set B, I don't know anything about the quality, I'll do all of this matching, and it actually tells me that they're rubbish at recording whatever variable. That's a very good point. That's great. Yeah.
Yeah, it's so in terms of kind of recommendations, we often, I would say it's a very good idea early in the record linkage process to build like a really kind of like quick and dirty record linkage model for the purpose of like building intuition about the data itself. So we do the profile, we work out like how null the data is, but then just that second step of looking at whether you get sort of like vaguely sensible M values out, it can be quite useful and give you actually insights into the data quality itself.
Yeah, I know. Thank you. I think what you've got there is just absolutely amazing.
Thank you.
Anyway, you can mute me now.
Sorry, I had to unmute. Thanks, Richard. That was a good question, and I have to think about this a little more, and I'm going to get in touch with both of you because it's a topic that I've been thinking about a lot lately. So I think we are bumping up at time, but Robin, I'm hoping you could answer Kara's question, and then we'll wrap it up. She has one in the Q&A.
Could you read it out, please? I can't see it.
Oh, sorry. We commonly have data sets with multiple addresses or multiple phone numbers. Can Splink match across multiple fields?
Yes. So yeah, again, this comes down to the customizability. So when you actually write those comparisons, define it as an exact match or define your like fuzzy Jarrow-Winkler match or whatever. if you want, you can write that as a SQL expression. And that means that you have access to any of the SQL, like the functions built into your SQL, like DuckDB or Spark or whatever. So certainly with DuckDB or with Apache Spark, one of the functions is an array intersection function. So that's taking in 2 lists of stuff, phone numbers, postcodes, whatever, and asking how big the intersection of them is. So that's so that type of comparison is actually built into Splink as well as like one of the out-of-the-box comparisons. But yeah, it supports an array intersection. And it's one that we quite commonly use for anything like that, which is like, yeah, there can be multiple values.
Great, thank you. I guess I lied. There's one more, hopefully a quick one. About how does Splink handle date comparisons with different formats?
Yeah, so there is a out-of-the-box comparison. So although you can write your own SQL, it's a little bit like fiddly, or at least you have to have a bit of an understanding of SQL. So we also provide these sort of out-of-the-box comparisons, which if we go back to the defining the linkage model slide, so where we've got a comparison here of like cl.jarrow-winkler at thresholds, under the hood, that's generating some SQL that says like case when surname is an exact match, then put it in this category. Case when the surname is a Jarrow-Winkler match of greater than 0.9, put it in another category. So that's the kind of SQL that you can write yourself if you want. For the date of birth comparison here, there's actually quite a lot of options which aren't shown here, but what those options do is they allow you to do things like if date of birth is held in your database as a string, not a date, it allows you to set the format for the date, which will allow the database to pass it into like a true date rather than a string as a date type thing. And what that means is simultaneously you can have different bins within date comparisons. So like we would tend to recommend there being predominantly 2 types. One being around difference in actual like date or time between the 2 dates. So is it a month different? Is it a year different? That sort of thing. So capturing like elapsed time. And then the other one being like a typo based one using something like Levenstein. And because like you can have the date passing where you're turning strings into dates or vice versa, you can simultaneously have all of those different categories for the date of birth comparison. Another common one that is supported here is 1st of January dates of birth. So in some types of data where data, like the exact birthday is unknown, people tend to put just the year of birth and 1st of January. So like as another example of customizability, you could put those into a separate category to sort of recognize the fact that if it's an exact match on date of birth, but it's the 1st of January, the model needs to be like a bit more skeptical about that than if it's any other exact match on date of birth.
Oh, that's amazing. And I think you have some really good documentation online too, right? I think
yeah, let me drop it in the chat. So this is the main homepage, which is currently Splink 3. It'll all switch over to Splink 4 soon. But one of the nicest things about the docs, which I'll put a direct link to, is you can try all this out in your web browser. So if I just get the right link, using Google Colab, we've got some examples where you can just click through the opening Colab links, and that will open, I can put it actually in the window I'm sharing. That'll open the example in Colab, and because we've built some synthetic data into Splink, you can immediately just give Splink a go in your web browser and see all the stuff I've been showing.
That's amazing, and I love all your graphics and your dashboards.
We've got an awful lot of work into them.
Oh my gosh, yes, it's actually amazing. And Richard gave a really nice comment about Splink. Like I'm amazed you got the time to develop it to the standard you have. I'm amazed also.
I've got the best job in the world.
Yeah, just fantastic. You can tell you're passionate about it and it's a labor of love. So yeah, I guess it's okay. Can you send me the slides and I'll send those to the folks who registered?
Yeah.
Thank you. Thank you so much, Robin. I always, like I said, learn so much from you. And I think I will definitely be in touch with you about some other things going on and areas of interest. So thank you again. And thanks everybody for attending, and have a great rest of the day and a good rest of the summer.
Great. Thank you all.
All right. Take care. Thanks, Robin.